Hey guys, Nate here. I just want to go through this Google Earth Engine app that I've put together to recognize forest loss, potential forest loss areas based on SAR data. This is very similar to what we looked at a couple weeks ago in our meeting. It's kind of an early version of this, and we're changing parameters and code. But I've put a little app together that has a little interface to it, so we can change the parameters here without getting into the code and messing with any of that. And I've made a couple of changes to the logic as well. So I just kind of wanted to run through that. I did run through this with Augustina last week, but I wanted to have something for her to refer back to and kind of show you guys how this is working. So again, the idea is that we're looking for areas with some significant drop in SAR backscatter values from one point in time to another point in time. So that drop in backscatter values roughly equates to an area that the sensor recognized as being a rough surface, like a tree canopy, and changing down to a smoother surface, like a pasture or just a recently lost area. So we're going to look at what I'm calling a baseline window to find kind of the previous state and compare that to an analysis window. Right now, the default that I have set up defaults to today and looks back at a 60-day window. In that 60 days, it finds the average backscatter, which helps to avoid a lot of the kind of noisiness of SAR data. So it finds an average, and it compares that to the average of the previous year. So that's my baseline. We can change that if we wanted to look at a smaller window. We could if we wanted to look at a larger window. Right now, 60 days gives us 4 or 5 different images to find the average for, which seems to be working pretty well. It's a good number to be working with. I'm going to go ahead and run this because it takes about a minute, and I'll kind of talk through some of these other things here. So this alert thresholds really kind of gets down to how we're recognizing significant change. So we're looking for the change in backscatter, and I'm saying the drop in backscatter. So right now I'm saying a change of about 3.5 seems to be a good number to start with for recognizing significant changes in backscatter values. We'll look at what those values mean a little bit in the chart, but 3.5 is working well. So if we boosted that number up a bit, we would probably find fewer areas. We would find fewer significant loss areas because it's essentially the sensitivity of this model. And then this is how big that area has to be for us to care and to kind of flag that as a loss area. So this analysis just ran, and we found 18 potential forest loss areas. I'll look at that in a minute. So this is how sensitive it is, how big it has to be, and then we're saying we're trying to limit the analysis to areas that were forested already. So you're going to see lots of kind of regular drops in SAR values for other reasons, and we looked at it. One big one was the drying and filling of the lake here. We don't care about that in this model. We just want to know about forest. I know there might be just agricultural patterns. If we went from a cornfield and then harvested that, we would change the backscatter quite a bit. But we don't care about those either. What we're just looking for is where the forest is. So those drops in expected current forested areas. I'm using Gedi to do that. So that's that lidar mission. And that LiDAR mission is roughly a 2019 vintage, and for using Gedi data, I'm saying anything that had every pixel is how high the canopy is. So in this case, I'm saying anything greater than 5. So I'm starting at 6 here. I'm going to consider forest. So any time that tree canopy height is 6 or greater, we're going to say that was tree, that was forest. We could drop that a little bit, but I think we're going to be picking up a lot of rastrojo areas, or we pick up a lot of extra areas that we might not care about. So you saw it took about a minute to run this, and this is what the results look like. There's a bunch of different results I'll kind of walk through here, but we do get this summary over here. It says we found 18 potential sites using these parameters. We could go over here, change it, and rerun it right away if we want to. And then we have some download options here, which we'll look at. This would basically pull it into a GIS package like ArcGIS Pro, QGIS, or something like that. And of course, KML will open in Google Earth. There's a bunch of different layers that this creates here. I'll go ahead and lock that layers list. Right now, we're just looking at these centroids. So these are little points that represent where those forest loss are. So there's 18 of those little points there. If we zoom in, we'll actually be able to see the area, but it's a lot easier to see as a point at this scale. So these layers here will help us kind of investigate and prioritize these 18 areas. First thing, let's look at this Gedi forest canopy height here. So this is again what we used for the mask. So basically, any pixel that's 6 or greater is being used as forest. And so the idea here is we want to find areas that, even in our 18 results here, is let's find areas that had some trees, kind of big trees to start with. So that might help us kind of prioritize these areas, right? So we want to look for areas that had big trees originally and then had some kind of drop. So that's potentially the loss of some big trees. I'm going to take a look at these 2 points here. Again, these points, as we zoom in a little bit more, you'll start to see that there are some areas drawing underneath with this kind of yellow to red ramp here. Red means that there's more backscatter loss. And the yellow will be a little bit less backscatter loss. So yeah, we do have these 2 areas here. I'm going to turn off that area just so we can kind of see underneath. Maybe these are transparency sliders, so maybe I'll just swipe those away. So it looks like there was some loss, and just smaller trees under this area to start with. But this one had some decent sized trees that there's been some kind of change, right? Let me zoom in a little bit more here. First thing we can do is experiment with this SAR time plot. You can click on any spot within the study area to see a time series for backscatter. So this is the area I'm kind of interested in. I'll go ahead and just click. We can click on any pixel, any area in our study area. And this reads that backscatter has decreased in the analysis window, so the 60-day time period, from the baseline, from negative 10.31 to negative 15, almost negative 16, a drop of almost 6 in its backscatter returns, right? And we can see it in the time plot, so it's always kind of hung around this negative 10 value. And all of a sudden, around March, we had a significant drop. So something happened kind of in this time period, right? And so it's saying that within this time window, compared to the analysis window versus the baseline window, we've seen a change. You can see that here. This is also going back to kind of the start of the Sentinel mission, which was 2017. This is going to be February of 2017. I can uncheck this, and it's going to show me just that time range of interest. So going back 2023 through May till today. And there's still a downward trend, but it looks like it's been trending for longer. But here's what we have for the entire time series. Couple of things I should point out here. Again, these are transparency sliders, so I can slide that back on. We do have, this is just going to be Google satellite imagery. The time on that is kind of unknown for most areas. But you do see that there's lots of trees whenever this image was taken. So we do have our own imagery that's being compiled from automatically, dynamically from Sentinel-2. So Sentinel-1 is SAR data. We'll look at these in a minute. Sentinel-2 is imagery. It's multispectral imagery. So I'm going to go ahead and turn these two on, and I'll tell you what these are. So it's automatically compiling a cloud-free mosaic for our analysis windows, or for the baseline versus the analysis window. So we have an image that's a year ago, and we have an image that's for the last 60 days. Okay. I'm going to, right now, the analysis window is drawing on top, and you can kind of see these areas here, right? You see something that looks like a burn or some forest loss, and that's for the last 60 days. So if I use transparency and swipe it away, we're going to see this is a year ago. I'm going to put the 60-day window back on top, and you're going to see these areas change, right? So just having that data, those images, is really powerful to be able to see that. Now, because it's building a cloud-free mosaic, I don't necessarily have complete coverage, and I'll just show you. So this is, I'll get rid of the baseline, because that's about a year time span. And let me switch this. And you kind of see what the coverage looks like for that analysis window. So for the last 60 days, trying to build a cloud-free mosaic is going to be very spotty. Right? So all these gaps are clouds. But we do have some good data in our areas. Like this one, we don't have data for imagery for the last 60 days. So that one's a little tricky. But again, we're not using multispectral imagery for this analysis. We're just using that multispectral imagery for reference, confirmation. We're using SAR data. That's what we're actually using to identify the change. So let's look at what that might look like here. So this is the SAR data. Lighter pixels are going to be higher returns, so those are going to be your tree canopy for the most part. Darker is going to be flatter, smoother surfaces. So here's our two kind of areas of interest, these deforestation or forest loss areas. And so I'm going to just, again, swipe back. So this is baseline, so a year ago. This is the last 60 days. And you're going to see, make sure you're looking right here to see that, look, we have some significant change. We went from lighter pixels to darker pixels between the baseline and the analysis windows. So it's kind of in confirmation of those results. Okay, so that kind of, I think we've kind of walked through what these are. This VV loss is going to be unmasked. So that's the backscatter loss, regardless of whether it was forested or not. I don't know how important that is. The forest mask is going to show us, based on the Gedi data, what it thinks was forested. So this is basically any green pixels are those that have a tree canopy height of 6 or greater. Again, those are just kind of those were done automatically on the fly when you ran the analysis. So it's just kind of confirmation. Make sure that you know what you're looking at here. Okay, so let's go ahead and look at these downloads. I think we've looked at all the other pieces here. Let's go ahead and look at these downloads. So I'll download a shapefile first. I'll download that as a zipped shapefile. Goes and puts a timestamp on that for you for your analysis window. I'll go ahead and download the KML too, which will just open in Google Earth later. So I'll start by extracting this shapefile, and we will just go ahead and pull that into ArcGIS Pro, drag the files in here, and now we have a polygon for each one of those areas. And I do attach some other information so that you can kind of help prioritize those. So we've got the area of loss, the amount of loss, and the average tree height based on Gedi within that polygon, before a forest loss event, obviously. So if we wanted to find the biggest, we're just going to sort this. So we're going to find, this is the largest area of loss, right? That's this one. So 6,000 square meters, right? Within that polygon, I'll go ahead and get rid of that the fill so we can see inside of it. So within that polygon, there was an average loss of backscatter of 3.7. And the trees inside of that, before any kind of loss, the average was around 11.6 meters. Right? So we have all those to work with. So if we wanted to find the polygon that had the most loss, right, just in terms of backscatter, the most average loss, that would be this one here. Okay, I think that's the one we were looking at earlier. And then if we want to find the one that had the biggest trees to start with, right, so these had 22.4 meter trees in it. I'll just zoom to this one, and we'll see what that one was. Right, so this one had some really big trees in it before any kind of before any loss event. So able to use that to kind of do some more queries inside of ArcGIS Pro, put it with some other layers before maybe sending people out to investigate that. Boots on the ground, or maybe a drone in the sky taking a look at exactly what happened. Again, we can take it into Google Earth Engine and look at the Sentinel imagery changes as well. So we have a lot of tools to work with to help us understand what's going on before actually sending people out. And I'll go ahead and open the KML so you can see what that looks like in Google Earth. So each one of these has that same information. Each one of these points has the size, the amount of loss, and the tree height within each one of those. Right? So again, just another way to visualize that. A little easier for non-GIS users to just pull this inside of Google Earth. So yeah, so I think that's it's pretty useful tool. I think there's probably some more sophisticated analyses that we could do to find some different forest loss areas. Although this is just using some really basic metrics of backscatter loss. I think we're doing a really good and efficient job of finding these areas of potential loss. And hopefully if you can send people out, take a look at these, maybe on a monthly, quarterly basis, to kind of confirm some of these areas with some photos and understand what's happening on the ground. So yeah, let me know if you have any questions. I guess bookmark this link, go check it out, run it a few times, see what you think, and let me know. Thanks.